All right, I want to finish off the scientific method. Where I finished last time was talking about experimenter bias. And here is a very biased experimenter, to say nothing of mad. This is Dr. Milo T. Pinkerton, the third musical mad scientist of this band called the Consortium of Genius that you ought to check out. Anyway, my sister's actually recorded some tracks with him, but later. Scientists are, as I was saying, we are human. We are not, mystical gods above the fray of mere human concerns. We have preconceived notions, we have biases, we have prejudices, we have things we really would like to be true and things that we really hope are not. We're just like everybody else. And we tend to get attached to our hypotheses and really want them to be true because that's freaking cool. Coming up with a really good hypothesis and seeing it get accepted by the scientific community is like, I imagine it's the way that a band feels when, after years of touring in a band and playing crappy little clubs, they finally, write a single that tops the charts. That's what that's like. What we're trained to do is to realize this, know that we are flawed individuals, and build experiments that eliminate as much of our own bias as possible. And I want to show you a famous example of this from history. There were a whole bunch of scientists, especially in the United States in the 19th century, who were absolutely convinced that people from Africa were mentally inferior to people of European descent. Europeans were at the top of everything, and then Asians maybe a bit below, and that left Africans and Native Americans fighting it out for last place. These are illustrations from a book that came out in 1954 by Josiah Knott, and I think his name was Samuel Glidden, Types of Mankind. Notice that up on top, you've got the white dude. That's actually a Roman sculpture of a god with this, great big brain in a great big flat face with an elegantly sloping nose. And here you've got the African guy down below with a smaller brain and projecting jaws and generally not looking nearly so handsome. And this was taken seriously by a lot of people. This was considered good science. This was the conclusion a lot of people reached. You may well be suspicious that it was reached based on biases, and you'd be right, and I'll show you an example. 1906, there's a doctor in Virginia named Robert Bennett Bean, who measured the sizes of various parts of the brain on 152 different brains from both Black people and white people. He dissected a lot of people and basically had a collection of pickled brains. I guess because, people need hobbies or something like that. And what he measured was, I say it's a particular part of the brain, it's actually a ratio between two different parts, two different areas of a giant nerve bundle in the center of the brain called the corpus callosum. We don't really need to worry about the details, but he had reason to think that if the ratio of these two brain parts was larger than a certain value, it meant you were smarter. So that's his data. Over on the lower part of the curve, that's his measurements for one of these brain parts. And on the left side of the curve, that's his measurements of the other brain part. And what I want you to see is that the open symbols right here, these white circles, are measurements of these two brain parts for white people, and measurements for Black people are represented by those black squares. And you'll notice that if you draw like a line right there, almost all of the white people's brains fall above this line, and almost all of the Black people's brains fall below this line. There's a little bit of overlap, sure, but most of the white folks are up here, and most of the Black folks are down here. And Bean had various reasons. We don't really need to go into exactly what they were for claiming that this showed decreased intelligence in people of African descent as opposed to people of European descent, because most Black people fell below that magic line and most white people had brains that fell above that line. Okay, Bean's old professor was actually suspicious of this. It looked too simple, and he measured another sample of brains, but did it without knowing what race they came from. He basically assigned every brain a code number and measured the brains based on the code numbers, and I think got somebody else to keep the code numbers, and then somebody else kept track of what races the brains came from. He just measured the brains and then got someone to tell him after he'd made the measurements whether they came from a Black or a white person. Okay, checking the chat. Okay, welcome Tyrone and Marissa. What he found was that when he didn't know what race the brain came from, he couldn't find any difference between Black people's brains and white people's brains. The whites here are represented by circles. The Black folk are represented by squares. And what I want you to see is that they overlap completely. There's no neat dividing line that you can draw between brains of Black people and brains of white people. And that's what I mean about bias. Bean, the guy who did the original work, this guy might not even have been trying to fool anybody. He might have been trying to be as honest as he could. But if you already believe that you're going to find a result, it's very easy to make yourself see it. We all have a tendency, regardless of race, to see what we want to see what we are sure is already there. And so Bean, using his little calipers to make the measurements, might well have just said, okay, this is a Black person's brain, and unconsciously might have squeezed those calipers just a little bit tighter. Or if he knew it was a white person's brain he was measuring, he might have just not pushed them quite so much, you know, rounded up just a bit more often than rounding down, something like that. You can do it, you know, even if there's no intent to commit fraud, you can, things like that can happen, even if you're, you know, if you're not consciously wanting them to happen. You know, we all have a tendency to do that. And that's why it's important to get experimenter bias out of the equation. What we learn to do is build experiments in such a way that we're trying, that as best we can, we immunize ourselves against our own biases. We try to design them in such a way that we're not seeing what we truly want to see. And Moll's work right here is kind of an example of the way we test drugs and vaccines right now. When we do clinical trials, you know, which is the type of experiment that you're probably most familiar with, we do them, they're called double-blind trials. What was it? We had something like 30,000 people that signed up for the very first clinical trials of the first COVID vaccine. When they went in there to get their shots, they were not told whether they were getting the actual vaccine or a placebo substance. saline water or something like that that should not have any effect at all. They didn't know. All they knew was that, they got an injection from a vial that had some kind of code number on it. And what's more, whoever gave them the shot, the doctor or the nurse or whoever it was, they didn't know either, because the behavior of the person giving you a medical treatment can influence how you respond to that medical treatment. If the doctor believes the vaccine's going to work and he knows what he's injecting, he might inject the real vaccine into the arms of some people and go, here's your shots, I hope you do well. And he might inject the placebo into the arms of other people and go, here's the shot. Or if the doctor's an anti-vaxxer, he might be tempted to inject the real vaccine and go, there's your injection of death venom, and inject it into the arm of the placebo into the arm of other people and go, here you go, you've escaped a horrible death. Behavioral cues like that can bias the results of a trial. And so the reason we do these things is so that neither the people giving the test, the doctor or the nurse, whoever is giving the shot, nor the patients who are getting it know what they're getting. They don't know in advance. That way, nobody's preconceived ideas, neither the doctors nor the patients, can influence the outcome of the trial. I mentioned that the vials that contain the injection that participants in the trial get, that vial is going to have a code number. Somebody back at the company that's running the trials has the code number, but the code number isn't revealed until the end. So we don't know until after the trial is over who got the actual drug and who got the placebo. And that's the way you build experiments to try to eliminate human biases as much as you can. The other way that you try to eliminate biases as much as you can is, first of all, you try to do things like large sample sizes. You would not test a vaccine on 5 people. You'd want to do it on tens, hundreds of thousands. The other way that I don't have a slide for, and I really should have, is something called peer review, in that once you've discovered something, you publish it. In the old days, this was done in print magazines called scientific journals. We still have some in the library. They're kept in the very quietest part where nobody seems to go these days. These days, of course, it's all on the internet, but you provide all of your findings to the scientific community at large, and other scientists are free to try to take it down, to repeat what you did or try something similar and determine whether you're likely to have gotten solid results or not. Sometimes this can result in a paper getting retracted. The study of that horse parasite drug, ivermectin, there was a study that tried to look at its effectiveness in treating COVID, but the study turned out to be done so badly with so many mistakes in it that the journal where the study was published ended up retracting it, taking it back. That happens. And each individual scientist may have various biases, but if you get a bunch of other scientists to look at everything and critically evaluate everything, you're much less likely to end up running afoul of one person's bias. So it's the fact that science is collective. We're all working on it together. And it's in the way that we design experiments that we keep the scientific process honest. So there are some aspects of life that aren't science. Any statement that you cannot put to some kind of test, experiment, observation, modeling, what have you, is not scientific. It's out of bounds. That doesn't mean that statements that you can't test are useless. It doesn't mean that they're wrong. It just means they don't work with the scientific toolkit. It just means that, they are flathead screws and you're using a Phillips. It means that they just don't work. This, by the way, is why we make you take other classes in the core curriculum so that you can learn to reason on statements and ideas that you can't really apply the scientific method to. So any statement that you can't test, and more to the point, any statement that you could never falsify is not science. Give you an example. These days, there are people out there that have decided that to argue that the Earth is actually flat, not round, not a globe like you were taught in elementary school, but in fact is a big pancake with the sun and moon kind of rotating around it. Okay, that's a hypothesis. That's a perfectly good hypothesis. The problem comes that people who hold this view construct it in such a way that there's no observation you could make that would ever prove it wrong. So, for example, if you say, okay, I watched a ship sailing away from harbor and I saw it vanish over the horizon, which only makes sense if the Earth is round, then they'll say, well, that's the atmosphere bending light. So then you say, okay, but we've taken pictures of the Earth from space. And they'll say, yeah, but those are all faked by NASA. And then you say, well, I've actually, you can say, I've actually flown around the world. I've actually been to Australia. And they will say, well, Australia doesn't really exist. It's all a hoax populated by crisis actors paid for by NASA. And so on. The hypothesis, the Earth is flat, is a scientific hypothesis. You can test it. It was tested back in the days of the ancient Greeks and rejected. Contrary to popular belief, Columbus and his sailors were not afraid that the Earth was flat. That had been established back as something on the order of 300 BC. The ancient Greeks were perfectly well aware that the Earth was round and did some very elegant experiments that confirmed that the Earth was round. The problem with the flat earthers is not that they think the Earth is flat. The problem is that the way they build their hypothesis is such that it cannot possibly be refuted by any means. There is no evidence that would ever satisfy them. And when you're at that point, you're not doing science anymore. And that's true of most conspiracy theories. They utterly fail at this because people argue for them in such a way that there is no way they could ever be proved false. A hypothesis to be scientific has to be open to the possibility that some evidence could demonstrate that it's false. Okay, there's a joke, by the way, about two people who are convinced that the 2020 election was a fraud. They happen to die at the same time, and they go to heaven. They get admitted by St. Peter, and they find themselves talking with Jesus. And one of them says, okay, Jesus, please tell us, what fraud did they commit in the 2020 election? And Jesus says, well, there was no fraud. It was a pretty honest election. And one guy looks at the other and says, the conspiracy goes higher than we thought. I'm not trying to get political here, and I certainly don't want to offend the feelings of people who believe in Jesus. But my point is that when you're that deep down the rabbit hole, nothing you could say would ever convince somebody that their beliefs are false. And if you've gone that far down, you are no longer doing science. And that's the fate of the, the flat earth conspirators and some of the anti-vax conspiracy theories that you're hearing these days. There's essentially no evidence you could ever provide that would convince these people they're wrong. That means they aren't doing science anymore. That's out of bounds. Okay, statements about artistic quality are also not the kind of things you can test with the scientific method. Now, things like popularity, you can. I could make a hypothesis that, I don't know, Beyonce's music is more popular than Taylor Swift's. And I could test that by going and looking at, number of plays on the radio, number of downloads on streaming services, things like that. I could do a popularity contest like that and I could test it. But often when we think about artwork, we think of greatness as some kind of intangible quality that it's got, but it's very hard to specify exactly what that is. So you might think that Beethoven's Seventh Symphony is more beautiful than Brahms's First, or we got a jazz bassist in here, so you might think that Charles Mingus's album, Mingus is better than anything Jaco Pastorius ever recorded, and that's fine. But statements like that can't be tested by the scientific method. Statements of aesthetics aren't necessarily wrong. It's not wrong to think about them. They're just out of bounds. They're not the kind of thing that your scientific toolkit can handle. Hypotheses also have to be stated very clearly and precisely. So a hypothesis like, when the sun shines on plants, like stuff happens, and like they all like do stuff, like, something like that you can't test. And a fair amount of junk science is junk, not necessarily because it's wrong, but because the hypothesis is so vague that you can't do anything with it. This is why a lot of branches of science use mathematics. And this is why branches of science use a lot of scientific vocabulary. We kind of go very easy on the math in this course, but certainly if you were studying physics or something like that, you would have to learn much more math. And I do what I can to keep the vocabulary down, but there's a lot of words in this class that you're going to need to know, and it is a pain in the neck. I've heard that a student in an introductory majors class, like our biology 1440, has to learn more vocabulary than a student in a typical foreign language class. And yes, it's a pain. The reason we use math and the reason we use fancy words is that they've got very precise meanings, and they let us talk precisely about the hypotheses that we're trying to test. And this is true for other fields as well. If your car mechanic says, well, the engine's not running right because stuff's happening in the thingy, okay, that does not inspire a great deal of confidence. What stuff is happening in what thingy? On the other hand, if the car mechanic says incomplete combustion is causing waste products to block your fuel injectors, okay, that's something you can tell what it means. Even if I'm not entirely sure just what a fuel injector is, I can ask him to show me, and he can talk about what's wrong with my car and why he's going to charge me double my mortgage payment to fix the thing. He can talk about that much more clearly than if he's talking about stuff going on in the thingy. And it's the same for science. It is a colossal pain in the neck to, have to learn the vocabulary to talk about, to talk about inhibition of acetylcholinesterase and the blockage of sodium channels. But that is a lot more testable than like stuff happens in your brain. Okay, so we need precise hypotheses. We can't really test aesthetics. Moral statements are not scientifically testable. Statements about what people should do. We sometimes call this the dichotomy between is and ought. Science is very good. It's the best, not perfect, but the best toolkit anybody's ever figured out for explaining why the natural world is the way it is. And it can predict what will happen if you do certain things, but there's no logical way that it can tell you what you should do. This is a little bit gross and maybe a little bit dark, but think about, okay, one person who is feeling down, feeling low, hates his life, and steps in front of an oncoming train. Think about a second person who's walking past the train tracks when he sees a toddler on the tracks right as the train is coming, and he dives and pushes the toddler out of the way at the very last second, but he himself gets hit by the train. Science can tell you how fast the train was going, what force it hit, the horrible damage it would do to this person caught on the train tracks. Science can give you all of those details. Most of us would probably find that the guy who saved the toddler did a very moral thing, a heroic thing, giving his life for someone else. We tend to believe that that is, morally very, one of the greatest deeds you can do. And the guy who committed suicide probably did not do anything nearly so great. In some religions, it might even be a sin. Certainly, it's not something to celebrate the way you would celebrate a hero that saved a life. That's probably the way most of you would feel about these. It's the way I would feel about them. Science, however, doesn't give you that answer. Science can deal with what does happen when somebody gets hit by a train. Science can't tell you whether you should risk getting hit by a train or not. That's what you need philosophy for. That's why we make you take other courses in philosophy and liberal arts and things like that. That's where you get the tools of reasoning that you need to deal with those. There's a very common logical mistake of asserting that something that is something that should be, that something that is natural is something that is moral. You hear this a lot in some circles. One example I can think of is, people should not be allowed to identify as transgender because that's unnatural. People should not be, I used to hear this a lot in the 90s. This is kind of, culture war is kind of faded now. But I used to hear a lot that, gay people should not marry because that is unnatural. Well, I don't want to tell you how to think about gay or transgender people. That's your own head you got to live in. But I am naturally so extremely nearsighted that without my glasses, I'm legally blind. Like if I take them off right now, I can barely read the screen 2 feet in front of me, and I sure as heck can't see anything else in this room. So naturally, I can't see worth a bleeping thing. That doesn't mean that because I'm naturally nearsighted, I should refuse glasses and go with the eyes that the gods have given me and, probably have a lot of car accidents and run into trees. Yeah, exactly. Just because something is natural doesn't make it a moral imperative. It doesn't mean I'm morally wrong for wearing glasses. And it doesn't mean that somebody who identifies as a gender that doesn't match their PP parts, it doesn't mean that that person should not identify as, whatever gender is closer to what they feel in their head. Again, I don't particularly want to tell you how you should think about such things, only to point out that appealing to a moral argument that appeals to nature is a wrong moral argument. Science ultimately does not give you moral reasons for doing things. Scientists can tell you all about how atomic bombs work. What they can't do is give you a moral reason for dropping them or not dropping them. That doesn't mean that such questions are not important. It just means you have to use other means of thinking to deal with them. And that's why we make you take all these courses in the core. You can't use only the scientific method to be a well-rounded person. All right, last one. Statements of religion, spirituality. Very important to many people, deeply felt by many people, and it's been that way all through human history, that people have felt very much that there is something more than just the physical realm of existence, that there are gods or spirits or angels or Lamassu if you are in ancient Sumeria, things like that, feeling that there is this non-rational, non-physical dimension towards life. Things like this may be deeply important to some of you. There are some scientists, I'm thinking in particular of this guy named Richard Dawkins, who published a book about 10 years ago called The God Delusion. And there's others who are pretty outspoken as atheists. The thing is, that's not a requirement to do good science. There are plenty of scientists who hold very sincere religious beliefs and follow them with conviction. I'm not going to name names, but I've been here at UCA since 1997. Back before some of you were alive, you young post-millennial whippersnappers with your avocado toast and your yeeting your TikTok YouTubes or whatever. Yeah, so I've been here for a long time. I've worked with a lot of people at UCA, and not everybody I'm going to mention is still here. A lot of them have retired or moved on. But in the time that I've been here, some of my fellow scientists in this department have been, some are Christians of, real faith and sincerity insofar as I can judge that sort of thing, that they go to church and they do walk the walk as well as possible, as far as I can see. I've had colleagues that are atheists and colleagues that are agnostics. I've had at least one that was Jewish, a guy who was a Sikh, a couple of people who at least were raised Hindus, one Buddhist, and a couple of pagans. We're all over the map, we scientists. And everybody that I'm thinking of, I'm not going to reveal names, but everybody that I'm thinking of has done perfectly good science that's solid and was supported and, supported by well-designed experiments and reliable observations and so on. And it doesn't seem to make that much difference in the quality of science that they do. The guy I used to work with who used to invite me to Easter services all the time did science that, as far as I could tell, was just as good as the casual atheist that I also used to work with. So plenty of scientists hold perfectly sincere religious beliefs, follow them, live by them. And I'm saying that because I'm never going to ask, but I'm pretty sure that some of you have very sincere and deep and strong religious beliefs. I'm not here to tell you that they're wrong. That's not what the state's paying me to do. And I'm not really here to take them away or try to refute them or anything like that. That is entirely up to you. That is your road to, that is your road to hoe. That's your walk of faith to take if you choose. Problems come when you take religious and spiritual statements and you try to test them with the scientific method, mixing up the two. And here's an example from way back in 1999. There was a surge of interest in clinical testing prayer. So a study that was published in 1999 in one of these scientific journals called the Archives of Internal Medicine took 990 patients that were admitted to the coronary care unit of this place, Mid-America Heart Institute in Kansas City. These were all people that were basically having heart attacks and brought into the ER. Okay, somebody's computer's about to die, so they're going onto their phone. That's cool. All right. Okay. What the researchers did was, as each patient was admitted, the patient was assigned randomly without being told to either an experimental group or control group. As much as possible, they tried to match the experimental with the control group. They tried not to put, all of the mild heart attacks in one group and all the really severe ones in the other group. They tried to make both groups as equivalent to each other as possible. The only difference was the experimental group's name were given to a local church's prayer team. Some churches have these. It's basically just kind of a phone bank. You call people and tell them, hey, Mr. So-and-so is in the hospital with a heart attack. Would you please pray for that person? And then they might call that person you've just called might call other people. And so everybody on the prayer team, stops, drops, and folds their hands and prays for whomever they're told to pray for. So the experimental group, unbeknownst to the patients didn't know, the experimental group's names got handed off to this prayer team who prayed for them for 4 weeks. And the people in the experimental group had a better average outcome. They spent fewer days in the hospital. They had a lower death rate and less of a chance of complications. On the face of it, this looks really cool. It's scientific proof of the healing power of prayer. And this is certainly something that a lot of people believe in. A lot of, every Christian church that I can think of, engages in the practice of praying for divine healing for the sick. Okay, have we proved it scientifically? Okay, we never prove anything scientifically. Have we confirmed it with an experiment? The experiment was done very well. They did everything right. There's nothing you can point to there. The problem is that any good science has to be repeatable. You have to be able to take an experiment and repeat it anywhere else in the world that's got the equipment and get the same results. And there were a bunch of follow-up studies following up on that Mid-America Heart Institute study in '99. And the problem was they did not confirm the results. There were, I know there was one study in California where they did find that prayer helped, but this being California, instead of giving everybody's name, everyone in the experimental group, their names didn't get given to just a Christian prayer team. They might get sent to a team of Christians or a team of Buddhist meditators or a team of Native American practitioners. And the results of that experiment were that all of those types of prayer seemed to help. On the other hand, other studies, at least 17, were reviewed in 2007. And the other study showed that there's no consistent results of prayer. Most of the times when you do this sort of experiment, the people that are being prayed for don't come out any better than the people that are not being prayed for. Does this mean you should not pray for sick people? I'm never going to tell you that. You know, if this is what your conscience and your faith tradition tells you to do, by all means, go and do it. What I'm telling you is that when scientists tried to look at this using the scientific method, you know, using well-designed experiments, the effect was not reproducible. They could not find it consistently when this was tried over and over again. In fact, there was actually one study in which patients who knew that they were being prayed for ended up with more complications than patients that didn't. This may have been an example of the reverse placebo effect. Think about it. You get wheeled into the ER and somebody tells you, hey, First Baptist of Texarkana has summoned its elite squadron of prayer warriors, and they're all praying for you. Are you going to think, hey, this is great, you know, I'm getting prayed for? Or are you going to think, oh my God, the First Baptist of Texarkana's prayer warriors have been summoned? I must really be sick. You know, you could take, you know, if you were told you're being prayed for, that might not actually be all that reassuring. Okay, by the way, First Baptist of Texarkana is so big, I'm told the locals refer to it as Six Flags Over Jesus. It's one of those really big churches. And I assume they've got, you know, top-ranking prayer commandos. But being told that people like that are praying for you isn't necessarily what you might, it's not as reassuring as it might seem. It's also extremely hard to design an experiment that's valid. All you ever have to do is say, Lord, I pray for healing on everybody who's in the control group, and you've completely destroyed the validity of your experiment. You know, you can't stop people who are in the control group from being prayed for. Now, you can make sure that people in a drug trial, if they're in the control group, you can make sure that they're not getting the drug that you're testing, but you can't make sure that people in a clinical trial of prayer are not getting prayer, right? Probably everybody in that trial had lots of people praying for them. So, you know, how do you know that it was the prayer of the prayer team that did it? I'll add that this adds some religious questions as well, because it raises the uncomfortable possibility that God might heal people on the basis of a popularity contest. You know, is God going to say, oh, wow, this guy's had a heart attack and he's being prayed for by the prayer warrior commando squad of the First Baptist Church of Texarkana, which is so big they call it the Baptidome. I'm going to heal this guy. Oh, but wait a minute, there's another guy over here who's had a heart attack, but only his family are praying for him and no prayer team is praying for him. Screw it, let this guy die. You know, that's not a very comforting picture of God, healing on the basis of how many people are praying. It's like healing on the basis of a popularity contest. I have no answer for that I'm going to give. You can figure that out by yourself if you want to. That's part of your own walk of faith. I only bring this up because blending science and faith gives you not only questionable science, it also raises some very difficult religious questions as well. They're questions that need to be thought of and thought about very hard if you're a believer who wants to, you know, do experiments like this. There. Little bit of gristle to chew on there. Again, scientists do not have to be atheists or agnostics. I've known plenty of scientists that weren't. I've known perfectly good scientists of, you know, all religious traditions. Religious beliefs among scientists aren't that different overall from religious beliefs in the population at large. And I can assure you personally that scientists feel amazement and awe and wonder and holy cow, this is incredible at the world. You know, scientists get a reputation as these very cement-headed, unspiritual people who are trying to reduce everything to a bunch of drab, boring numbers and figures and equations. Scientists feel just as much wonder at the things that we study as anybody does. You know, if you're an astronomer, you are allowed to look at a picture like this and say, whoa, that is amazing. That is majestic. You can be a Christian astronomer and quote Psalm 8 if you want to. When I look at thy hands, what is man that thou art mindful of him? But it does mean that when scientists are doing science, we try not to blend science with the supernatural. The two are not necessarily wrong. They're not bad ways of looking at the world. Mixing the two leads you to poorly done science and sometimes very off theology as well. So, you know, maintaining that kind of division is probably really important for science to be able to work the way it should. And I will just leave it at that, but we're going to go on to something else. I'm checking the chat. Ian says, wasn't Galileo a Christian? Galileo was. I mean, he ran afoul of political problems with the Pope at the time, but he was perfectly devout. Isaac Newton was. The guy who came up with the model of how the universe originated, that's now commonly called the Big Bang. The guy who came up with that was not just a Christian, he was a Catholic priest. Charles Darwin, of all people, had studied for the ministry. By the time he published his ideas, he was pretty much an agnostic, but he certainly wasn't ignorant of Christianity at all. He was almost a minister. Yeah, I think the library's got a pretty good book by a cell biologist named Ursula Goodenow called The Sacred Depths of Nature. And there's others like it if you personally want to explore the interface between science and faith. I'm not going to say more about it. That is entirely your walk to walk if you so choose. But it's out there. There's a lot of interesting stuff to explore. But we can't keep going here. I'm going to step back and we got to talk about something else. Right. That's what I've got about what science is. In the time that we've got, let's talk a bit about what life is, since biology is, after all, the science of life. Okay, quick random question. Somebody was asking about the textbook. The only thing you've absolutely got to buy is a new copy of the Biology 1400 Laboratory Manual. The lead author on that is Krista Peppers, although I'm also one of the authors because I wrote one of the labs. That has to be bought new and you can pick it up at the usual places. You don't have to buy the textbook as such unless you feel like it. It might make a good thing to read for review purposes. If you don't find my lectures perfectly clear, you might want to cross-check them against what's in the book. Some people learn better when they try multiple ways, but I'm not going to force anybody to have it. All you're tested on is what pours forth from my golden tones. And yeah, the lab manual is $40. You're only going to need it on your lab day, and labs don't start till the week of September 12th. So you've got something between a week and a half and 2 weeks before you need to actually have it in your hot little hands. Okay. Allowed to wear open-toed shoes on wear whatever you want. You know, the lectures are all done virtually you don't have to wear pants if you don't want to. I mean, if you're on campus, you probably should, but if you're kicking back in your dorm room, you can listen in buck naked if you want, or dress like a banana, or one of the Avatar aliens if you feel like it. In lab, we're going to ask you to try to wear closed-toed shoes, just because there's always a risk of dropping something, maybe breaking glass and having it cut your feet. I don't personally do spot checks. This is not boot camp or anything like that. If you insist on wearing sandals, we're not going to kick you out, but it's just something we want you to do for your personal safety. We don't want you to get cuts. All right, I need to, I'll check the chat one more time, but I kind of need to, no, I'm not going to dress like a banana, sorry. You're not, yeah, your tuition's not paying me enough for that. Sorry if that disappointed anybody. Let's go on. Let's look at what life is. We'll run into some things in the course of the course that are not entirely living. The example that's on everybody's mind right now is viruses. I can't fully explain this until we've covered some more ground. We will be talking about viruses about 3/4 of the way through the course. But viruses, the question as to whether they're living or not is kind of an interesting philosophical one, because they don't tick all of the boxes of a living thing. And we can find some entities in this world that are sort of like living things, but not entirely like living things. No, the banana suit is dead, ruled out. Don't even think it. The banana suit has no appeal. Right, shut up about the damn banana suit. We'll find some things that don't check all of the boxes on whether something is alive or not. There is a kind of fuzzy middle ground there. And certainly, when we're able to explore the planets more, I know people that work for NASA and spend their time thinking about exactly how do we define life and how would we recognize it if we found it on some other planet and it didn't look familiar. Life on other planets is not going to look like people with ridges on their foreheads. Life on other planets might look really strange in ways that we can't guess right now. So how would we even know that it was living? What we can do is come up with this common set of features of living things on Earth. One of them is, one of them is living things share a common chemistry. Living things on Earth as we know them are made up almost entirely of the elements carbon, hydrogen, oxygen, and nitrogen. I'm assuming you've had some chemical background and you know a bit about atoms and chemical elements. Those 4 elements make up about 96% of your mass. We also have to pay attention to the elements phosphorus and sulfur. They only make up about 2.5% of your mass, but they are very important structurally for reasons that we will see later. So these 4 elements, CHON, carbon, hydrogen, oxygen, nitrogen, plus 2 more important elements that are not as common, but critical for reasons, potassium and sulfur, or phosphorus, sorry, and sulfur, make up most of your mass. And the mnemonic here is schnapps, if you want. There's lots of other elements that living things need. Your body needs iron and zinc and magnesium and calcium for healthy bones, and sodium and potassium, because that's your electrolytes and that's what plants crave. They're also important, but the vast bulk of living things is schnapps. I don't have time to go into detail as to why it's those, except to give you kind of a metaphor. atoms of those CHNOPS elements are kind of like basic Legos in that they can bond with each other in lots of different ways. Elements like gold, those atoms don't stick to many other things in many different ways. Those atoms are like the helicopter rotor in a Lego kit. There's really only one thing you can use that for. CHNOPS are like those 8-dot and 6-dot and 4-dot Legos. You know, you have enough of those and you can build the Statue of Liberty life size. You can link those together to make structures that are, I can't say infinitely large, but indefinitely large. You can link those together in a ridiculously large number of ways. Living things put together atoms of CHNOPS to make a huge number of complicated molecules. Molecules are what you get when you stick atoms together. And living things, or organisms as we call them, organism just means any living thing. They take in energy and matter from outside and use those to build up and break down their own molecules. Building your own molecules is called anabolism. Breaking down molecules is called catabolism. And the sum of the two, put them together, and you have metabolism, a term that you might be familiar with. Metabolism is this constant chemical process of breaking down and building up your molecules. There are some molecules that make up your body that are really small, like H2O, water, but some of them get extremely large and complex. This picture is a diagram of one of them. That's a diagram of a big complex molecule called a protein. There are also molecules called carbohydrates, lipids, which includes fats, oils, and waxes, and nucleic acids. That's the four main classes of really big molecule found in all living things, what we call macromolecules. We won't have time to discuss all of these in very close detail. I am going to make you absolutely sick talking about proteins and nucleic acids starting a little bit after halfway through the course. You're going to hear more about those than you ever dreamed. Those macromolecules aren't just floating around at random. They're organized into structures called cells. This is something you're actually going to see in one of our labs. This is the leaf of a water plant. And if you look at it under a light microscope, it looks like it's divided up into little boxes stuck together. So there's a box, there's a box, there's a box, all a bunch of little boxes stuck together. You can think of the cell as the smallest unit that can carry on metabolism. Some living things are made of just one cell. You are made of roughly, I think, 17 trillion, give or take. And each cell carries out its own metabolism. Cells, of course, can work together to do lots of different things. They certainly do in your body. Each cell stores genetic material. I'll talk about that in just a second. And every cell is bounded by a flexible membrane, a very thin outer sheet-like covering called the plasma membrane. And some things that the cell needs can get through the plasma membrane, and things that the cell doesn't need can be kept out. So this plasma membrane defines the inside of the cell and defines what is on the outside of the cell. Okay, what those cells contain is lots of things, but one of the critical things that they contain is a macromolecule called deoxyribonucleic acid, or if you don't want to say deoxyribonucleic acid, we can just call it DNA. And I'll be talking about this in painful detail that will make your eyes fall out of their sockets in about halfway through. let's say right now that DNA is a molecule that can carry information. It carries information in a type of code. We call it the genetic code about what a living thing is and what it can do. You have the shape that you do, and you have the metabolism and lots of other abilities that you do because they're specified in very large, very long and complicated molecules called DNA. And we will talk later as to exactly how this works. DNA is what we call the genetic material, and using this DNA, living things pass on their features to future generations. In part, you've got the skin tone and build and eye color and hair color and even tendencies to certain diseases that you do because you inherited them from your parents. You didn't literally inherit them from your parents. You have them because what your parents contributed to you is pieces of their DNA. And we call this phenomenon of passing on traits from one generation to the next is called heredity. And we'll talk about that in much more detail coming up soon. Living things are also capable of monitoring and regulating their own internal processes to maintain a stable state. If you get cold, you start shivering, and that generates heat to keep your internal body temperature warm. If you get hot, your skin capillaries expand, so you look kind of flushed, and you sweat, which evaporates, and that keeps you cool. So you can go from being very cold to very hot to very cold on any given day, and your body still is able to maintain a stable core temperature of about 37 degrees Celsius or 98.2 degrees Fahrenheit. And your body does the same thing with how acidic or how alkaline your blood is, what your blood pressure is, your water balance, whether you've got too much or too little. Your body does lots of things to regulate those balances. And that balance is what we call a state of homeostasis. Stasis means staying in place. Homeo is similar in Greek. Homeostasis means staying in a similar state, regulating your internal conditions. Organisms can sense their environment and respond to it. Even plants can sense where the light is coming from and where the gravity is coming from. So they grow their roots down and their leaves up towards the light. Some animals even have senses that humans don't have. That's a prairie rattlesnake, and these pits, that pit that I've just circled, which is under the eye, detects infrared radiation. It gives these snakes a type of night vision. That's how this snake can strike, kill, and eat a helpless little desert kangaroo rat in the middle of the night when it can't see. Yeah. So living things can sense their environment. The features that you find in a population of living things can shift over many generations, and we call this change over time evolution. I should mention that evolution does not cover changes over a single organism's lifetime. You were all once little balls of cells, and then you became screaming newborns, and then bratty toddlers, and then surly teenagers, and now fine upstanding young men and women. And eventually you're going to become geezers, and then you're going to die. That's life, but that's not evolution. The things that Pokemons go through is not evolution. I know they call it that, but we're not talking about Pichu becoming Pikachu, becoming Raichu, or Charizard becoming Flamo Lizard, becoming Burno Godzilla, or whatever the hell it is. My kid knows, I don't. That's not evolution. Evolution is change over many generations in response to changes in the environment. This lets a species adapt to its environment, and a species that can't do that can end up like T-Rex over here and become extinct. And then the last thing, I know I am almost out of time. I've got about 30 seconds, but the very last thing is every organism interacts with other living things in its environment and with things in its environment that are not alive, like the light, the water, the temperature, things like that. Every living thing's connected to other living things. There's no such thing as a lone organism. Living things eat each other. Living things make each other sick. Living things depend on each other, like bees and flowers. The study of all of this together, which will occupy us in the last couple of weeks, is ecology. So every living thing is connected to other living things through a set of ecological relationships. And on that note, I will stop the recording.